In this video, I'm going to talk about the Friedel Crafts Acylation reaction, which belongs in the category of electrophilic aromatic substitution reactions. I'm going to start off with a generic example, and then go through some more specific cases, and then finish up with a detailed walkthrough of this mechanism. Okay, so starting with the Friedel Crafts Acylation reaction, we're always starting with an aromatic group, so benzene or related derivative, and we're going to add to this an acyl halide, or you might be more familiar with acid halide. In this case, we have an acyl chloride. So notice we've got carbon-oxygen double bond attached to a chlorine. This is called the acyl group when we have RC double bond O. And we're going to add a Lewis acid to this. And in this case, the Lewis acid that I've chosen to show is iron trichloride, FeCl3. There's other Lewis acids we can use for this. We'll talk about that. And the product of this reaction is a ketone. So we have got a species where we've got a carbon-oxygen double bond attached to two carbons on either side. This is called a ketone. And the key bonds that are formed and broken in this reaction are we are breaking carbon-hydrogen and we are forming carbon-carbon. And this is occurring on the same carbon. So because of this, when we're swapping one group for another on the same carbon, we call this a substitution reaction. And because this is happening on an aromatic ring, we call it an aromatic substitution. And because we're adding an electrophile, we're adding an acyl chloride, this is an electrophile, we call this electrophilic aromatic substitution. Okay, so in this process, like I mentioned, FeCl3 is simply used as an example. We can use other Lewis acids. A common one is also aluminum trichloride, AlCl3, and we'll show a couple more specific cases down here. All right, so here's a really general case. We'll start with benzene again, and we'll add our acyl chloride in presence of iron trichloride. Notice our product here is our ketone. We're forming and breaking a bond on the same carbon. And I haven't shown it here, but the byproduct of this reaction is hydrochloric acid, HCl. Okay, and so fairly straightforward, exactly the same as the example above. Nothing much more complicated than that. Okay, let's look at another example here, and let's make things a little bit more complicated. So instead of starting with benzene, we'll start with a substituted benzene. So in this case, chlorobenzene. And we'll add our acyl halide. In this case, I have an acyl bromide, and we usually use a brominated Lewis acid in these cases, aluminum tribromide, for example. It's not super crucial that you match the halides together with your Lewis acid, but we do it for obscure reasons that we won't get into. Now, the product of this reaction is, again, the same as before. We're forming a carbon-carbon bond, we're breaking carbon-hydrogen, but because we have a directing group present, this is going to affect which product we obtain. And halides, chlorine, for example, is a ortho-para director. So it is going to give us the products for the para substitution, which is what I've drawn here, as well as the ortho substitution, which I didn't draw, but is also a byproduct of this reaction. And one further note is that chloride, because it is a deactivating group, it takes electron density away from the aromatic ring relative to hydrogen. It's going to be a slightly slower reaction than it would have been with simply hydrogen here. Okay, slightly different example. Let's start with an activating group, so OCH3, methoxy. And again, taking our acid chloride in the presence of a Lewis acid, we're going to do our electrophilic aromatic substitution. We will form, in this case, because O-methoxy is an ortho-para director, we're going to get the para product as well as the ortho product, which I haven't drawn, but is just the position next door to the OCH3. And of course, we're going to form HCl as a byproduct of this reaction as well. This next example is one that might be sometimes confusing to students the first time they see it, because we're really only starting with one product, or one reagent. We're starting with this molecule, and then we add iron trichloride. And if you're expecting to see two different molecules being added together, I could see how this might be a little bit confusing. So what's happening here is that our benzene and our acid chloride are actually present on the same molecule. So when we add iron trichloride, what we're going to do is we're going to activate the acid chloride, which is here, to react with our benzene ring, which is here. And in the process, because they're all connected together through this carbon chain, we're going to form a ring. And that's our product here, this cyclic ketone. So this is an example of an intramolecular reaction. And again, our byproduct, which I haven't drawn, is HCl. This last example is worth showing simply because there's situations sometimes where the Friedel Crafts reaction doesn't work very well. And one case is when we have a very deactivated aromatic ring. For example, if we have a nitro group present on our aromatic ring, this is going to take down the electron density of the aromatic ring, and this is going to slow this reaction down to the point where this reaction actually does not occur. So when you see an example with a nitrobenzene, this reaction is actually not going to happen. Okay, so let's walk through the detailed mechanism of this reaction. So starting with our acid chloride, when we add iron trichloride to our acid chloride, what's going to happen is, and what happens with all of these electrophilic aromatic substitution reactions, is that our electrophile, in the case of this reaction, our acid chloride, is an okay electrophile, but the Lewis acid is going to make this an even better electrophile. It's going to make it even more electron poor. And we'll see how this occurs, because the chloride is going to donate a pair of electrons to the iron to form a bond, and we're going to end up breaking the carbon-chlorine bond so that we form a carbocation on carbon 1. And this carbocation, which we call the acylium ion, is more electron poor than the species that we started with, which is the acid halide, and therefore more reactive. So it's a more reactive electrophile. We've taken electrons away from it. And benzene, which is normally not reactive enough to react with acid halides, will react with the acylium ion because it's a stronger electrophile, a more electron poor electrophile. And that's what happens in the second step, which is the actual electrophilic aromatic substitution itself. So starting with benzene, we take a pair of electrons from the pi bond of benzene, and we form a bond to carbon 1, forming a carbon-carbon bond, and we, in the process, generate a carbocation. And the carbocation is unstable. This is the rate-determining step of the electrophilic aromatic substitution reaction. We're breaking aromaticity to form this unstable carbocation. And once we've done so, now a chloride ion from the iron tetrachloride that we formed in the first step can then take a hydrogen away from carbon 2, and we can regenerate our carbon-carbon pi bond and therefore regenerate the aromaticity of the ring. And so this is the end of the reaction. You notice what's occurred is we've swapped hydrogen for carbon, and our byproduct here is hydrochloric acid, and we've also regenerated iron trichloride. So our catalyst has been regenerated. So this is so we've walked through the generic example of the Friedel Crafts acylation reaction. We talked about a few specific examples, especially the intramolecular case and the case where it's 2D activated to work. We walked through the mechanism, and if there's any questions or comments you have at the end of this video, I'd welcome you to leave a comment or a question below, and I'd be happy to address anything you have. Thanks for watching.